Hello, and this is my Lab 4 physics lab on oscillations of a spring. In this lab, we observe the motion of a spring oscillating in 2 dimensions, and we model that motion using v-idle and Newton's second law. We also look at how which period we use affects the prediction and the model of our oscillating spring. Here's the video of the spring that we're modeling. Right, and now we have a lot of formulas for this lab. First, we need to figure out K, the spring constant, and our L sub O, which is our spring at rest. To find out K, we first find the period by just looking at the motion and observing the changes in the motion, and then we use this equation, and then just derive that to get our K, which is 4 pi squared times mass over the period squared. Then we use that K in this, and we know that the force of gravity is going to equal the force of the spring when the spring is at rest. And we already know that our L, when the spring is at rest with the mass on it, is at 0.7 meters. So we just plug in all of our values, and then we get our L sub O. Now, when I did the math, when I used the period of y, I got a K of 6.869 Newton meters and an L sub O of 1.26 meters. For x, I got a K of 5.829 Newton meters and an L sub O of 0.024 meters. And we'll look at the differences between those and how they affect the model later. Calculating F net for this lab is pretty simple. We just take our force of spring plus our force of mass, or force of gravity, sorry, and then get our F net. Then we use Newton's second law, as we have in many other labs, to calculate the velocity and also to calculate the position. Velocity final equals velocity initial plus F net over mass times delta t, and then our position final is equal to our initial position plus the final velocity times delta t. Now, we also introduced the energy principle in this lab, which is the change in energy is equal to the change of all the energies. In this lab, because our system is the ball, the mass, the spring, and the earth, this delta E should equal 0. So these all need to add up to equal 0, and we'll see how they do later in lab. And to find all these energies, kinetic energy, it's 1/2 times the mass times velocity squared. Our potential energy of gravity is our mass times gravity times the y. And our potential spring is 1/2 times the spring constant times the displacement squared. So let's look at our code here. As you can see, the mass of the ball I found would be 0.42 kilograms, taking that from our video. And then this is our initial position. Our delta t is 1 over 2 to the 10, 1 over 2210, 1 over 210. Our spring constant is 6.869. This is using the y period of oscillation, and a 0.126 for L sub O. I found the y to be more accurate, that's why we're using this one. Our energy formulas are just right there. And then we just plugged in all of our equations into our code right here. And now we run that. So you can see the red ball is the actual motion while the blue ball is the predicted. As you can see, they're just about very accurate and follow each other very closely. Now this is our graph of our energies. Our blue is kinetic energy, our red and green are two potential energies, change in potential gravitational energy and potential spring energy. As you can see, they cancel each other out as the graph goes through, and that's why we get a total energy of 0, which is this yellow line right here, constant throughout the entire graph. Which, leading back to our what does it mean question, the energy principle is satisfied because the change in kinetic energy is 0 because there was no energy leaving or entering the system. Now, for our period using the x and our period versus the y, I also modeled our period when we use the x period, and I have this, and we get this prediction. As you can see, they start off pretty close, but they pretty quickly split up and change. You can see it even better on this graph. This is actually modeling the change in position of the two, so you can see how they start to split apart and don't actually follow the same path anymore. I'm not really sure why this is so, but it's just the nature of the way the spring oscillates in the x direction. Thanks for watching.